Hey guys, welcome back to my channel, Math Sprint, and you are watching the sixth video of my calculus crash course. Today I'm going to be explaining some applications of differential calculus. In this video, I will be delving into critical points, concavity, mean value theorem, Rolle's theorem, and Hopital's rule. Before we begin, make sure you're familiar with at least these concepts, which will be very important if you want to understand this chapter in calculus. So first understand these concepts and then continue with this video. The topics to know are basic algebra, polynomials, set notation, straight line graphs, how to plot a graph on a Cartesian plane, functions, limits, and continuity, differentiation and its fundamental rules, and how to perform differential calculus on different types of functions. Also, do note for this chapter of calculus, I will only be working with real numbers and not imaginary numbers. So do keep that in mind. Also, before we begin, I need to tell you guys that I will be using interval notation in this video. If you don't know what interval notation is, I'll explain it a little in brief. Interval notation looks a lot like the notation used to indicate a set of coordinates on the Cartesian plane. It's important to understand the context of the given problem, and that way you can tell whether an interval is being shown in the problem or a set of coordinates. So let's assume that you have a hypothetical problem where you get an interval. So let me explain the meaning of each notation. The parenthesis, like over here, indicates an open interval. So a comma b in parenthesis, as shown over here, it won't denote coordinates in this context, but instead it'll indicate that the set of all values between a and b, but not including a and b. Whereas the square brackets, like you can see over here, is indicating the set of all values between a and b, inclusive of a and b themselves. So let's start the actual work. Let's start the actual chapter. Increasing functions. A function f is said to be increasing on an interval if f of b is greater than or equal to f of a, where b is greater than a. So if we link this idea to calculus, then we have to say that a function is increasing if f dash of c is greater than or equal to 0, where c lies within the specified interval. In mathematics, the word increasing is actually different from strictly increasing. If a function is said to be strictly increasing, then f dash of c is just greater than 0. F dash of c is never equal to or less than 0 in the specified interval. Now, decreasing functions. So a function f is decreasing on an interval if f of b is less than or equal to f of a, where b is greater than a. Again, we can link this to calculus. We say that a function is decreasing if f dash of c is less than or equal to 0, where c lies in the interval. And if we say that a function is strictly decreasing, then f dash of c is just less than 0. F dash of c is never equal to or greater than 0. So let's do a problem to test your understanding. You might want to have a calculator with you for this problem. So the question is, find the open intervals for which the graph on the right, that is over here, is strictly increasing and strictly decreasing. So remember, the question is asking you to find open intervals and not closed intervals. So just keep that in mind when you get the final result. So the equation associated with the graph is f of x is equal to 2x cubed plus 3x squared minus 7x. So let's calculate f dash of x. You just use the rules of differentiation, and you get f dash of x is equal to 6x squared plus 6x minus 7. Now, if you notice in the graph, there are 2 points where f dash of x is equal to 0, and these points are sometimes called turning points. So over here is one turning point, and over here is another turning point. The first point which is in the second quadrant, is the point where the function stops increasing and it starts to decrease as you move across the x-axis from left to right. And this second turning point in the fourth quadrant is the point where the function stops decreasing and starts increasing after a certain point, as you keep increasing the value of x. So to find the open intervals, we have to first find these turning points first. So f dash of x is equal to 0 here. We use the quadratic formula to find the roots of this quadratic equation. So we get x is equal to minus 3 plus or minus root 51 by 6. So here you just use the calculator to figure out that x is about minus 1.69 or x is about 0.69. So now we can find the intervals. We use the graph to help us determine the intervals. So we find that f is strictly increasing over the open intervals. X is greater than minus infinity and less than minus 1.69. And it's also increasing for x is greater than 0.69 and but less than infinity, because the gradient, if you notice, the gradient of the graph is actually increasing over these specific intervals. Whereas for the functions actually strictly decreasing over the open intervals between minus 1.69 and 0.69. So over here, it's strictly decreasing because the gradient is negative over this interval. All right, let's move on to concavity. Concavity focuses on the rate of change of a function's derivative. So a function is said to be concave up if f double dash of x, remember the second derivative, f double dash of x is greater than 0, and it's said to be concave down if f double dash of x is less than 0. So functions can be concave up over some intervals, but concave down in other intervals. For example, if you look at the graph of, say, f of x is equal to x cubed, this is concave down for all negative values of x, but it becomes concave up for all positive values of x. So concave up, you can think of it like it's saying that the graph opens upward, like over here, if you notice in this image which I'm indicating with the mouse. So concave up means the graph opens upward, whereas over here it shows that concave down means the graph opens downward. All right, here we are, critical points. Critical points are specific points within the domain of the function f, where f dash of x is equal to 0 or f dash of x is undefined. So if you take the graph over here on the right, the equation of the graph is y is equal to x to the power of 2 by 3. The critical point is at x is equal to 0, which we can find using calculus. But the function is not differentiable at x is equal to 0. So since f dash of x doesn't exist at x is equal to 0, x is equal to 0 is the critical point of this function. Also, you should know some terminology. A stationary point, which I'll be explaining later, a stationary point is a type of critical point where f dash of x is only 0. That's a stationary point. So since I brought up stationary points, I'm going to be delving into the types of stationary points. Remember at the station, like I just mentioned before, a stationary points exist at wherever f dash of x is equal to 0. There are three types of stationary points. The first one, the local maximum. So a local maximum is basically a turn, you can think of it like a turning point, where the graph's gradient changes from positive to negative. As a result, the local maximum is often greater than the points adjacent to it. So if this is the local maximum, then the points adjacent to it will always be below the local maximum. So also note that at the local maximum, the graph is concave down only, which kind of makes sense if you think about it. If this is the local maximum and all the points adjacent to it are below the local maximum, then logically it should be concave down. So the second one is the local minimum. The local minimum is a turning point where the graph's gradient changes from negative to positive. So as a result, the local minimum is often like less than the points adjacent to it. And again, like using the same logic I mentioned earlier, at the local minimum, you can figure out that the graph is concave up only. So since the points adjacent to the local minimum are greater than the local minimum, it'll logically be concave up like this. So the third stationary point. The third stationary point is called a stationary inflection point, or sometimes just called the inflection point. The stationary inflection point is the point where the concavity of the graph changes. So if we're talking about concavity, you should remember what I told you about the double derivative. That is the second derivative. So if the concavity of the graph changes at the inflection point, then the second derivative of the function changes from either it changes from positive to 0 to negative, or it changes from negative to 0 to positive. So essentially, at the stationary inflection point, f double dash of x is 0, but also f double dash of x changes sign from, say, positive to negative or negative to positive across this inflection point. All right, so stationary points exist at f dash of x is equal to 0. And this fact allows us to identify where the stationary points are located. But how do we classify stationary points uh, as local maxima, local minima, or stationary inflection points? So there are two ways. The first one is the first derivative test, which I'm showing right now. So these are the three steps to be able to use the first derivative test. The first step is to find where the stationary points are. The values of x where the stationary points are located need to be calculated by equating f dash of x and 0, and then solving for x. Then you have to calculate the value of f dash of x for values of x a little before the stationary point and for values of x a little after the stationary point. So let's suppose that we have a scenario where the stationary point is at x is equal to 1. We know that f dash of 1 is equal to 0. So we calculate f dash of x for a value of x that is slightly smaller than 1. For example, 0.999. That's like the difference between 0.999 and 1 is just 0.001. So we check if the value of f dash of 0.999 is positive or negative. Then we take a look at this table. After that, we calculate f dash of x for a value of x that is slightly larger than 1, such as 1.001. And if we check the value of f dash of 1.001, we have to use this table after determining whether this value is positive or negative. So again, let's take this scenario where f dash of 0.999 is negative and f dash of 1.001 is positive. Then we can conclude that x is equal to 1 is a point of local minimum by looking at the table over here. So you should probably note down this table. The reason why we can figure this out is because before the stationary point at 0.99, the graph has a negative gradient, but after x is equal to 1, the graph has a positive gradient. So what does this indicate? As per the definition of the local minimum, we can figure out that logically that the graph is concave up, and also it's a point of local minimum. So the table on the right basically shows the conditions for which a function f has a local minimum and a local maximum. You just note down this table or take a screenshot, and essentially you should be able to use this table as a guide to be able to identify whether it's a local maximum or local minimum, depending on these conditions. All right, the second derivative test. The second derivative test is like another way of classifying stationary points. The first step is the same as that of the first derivative test. So first you have to find the stationary points, obviously. Then you use differentiation to find the equation of f double dash of x. You plug in the critical point, which we're taking as c, just some critical point, into the second derivative function. Then you check if f double dash of c is positive or negative. If f double dash of c is negative, then the function's concave down. And if it's concave down at the critical point, then you know what that means. It's a low point of local maximum. And if f double dash of c is positive, then the function is concave up, and x is equal to c is a point of local minimum. Suppose if we get a scenario where it's an inconvenient one if you don't really like math. Suppose if f double dash of c is equal to 0, then we need to calculate the value of f double dash of x for a value slightly smaller than c and for a value slightly larger than c. These are a lot like the steps I described for the first derivative test. If the value of f double dash of x changes sign across c, that is, in f double dash of x changes from positive to negative or negative to positive, then this is a stationary inflection point. Now, remember, if f dash of x is equal to 0, then it's a stationary point, which is another type of critical point, basically. But there are other types of critical points, as you must to figure out. Now, none of these critical points on this slide are stationary points. because for all of them, f dash of x is undefined at the critical point. So the first one on the top left corner is an example of removable discontinuity. It's like a hollow sphere at a specific point. This is a critical point because the function is not differentiable at this point, which in this case is x is equal to -2. The function is not differentiable because, first of all, the function is not even continuous. So if you recall in one of my previous videos, I had explained about the conditions for differentiability, and one of them is that the function has to be continuous. So the next one over here is an example of jump discontinuity, because over here, x keeps increasing from, say, this is a hypothetical scenario, x increases from 0 to 2, it jumps and then continues all the way along this curve, all the way along this line, endlessly in that direction. But there's a jump at x is equal to 2. And this is a critical point because, again, the function is not differentiable at the point where the jump takes place. So since f dash of x is undefined, x is equal to 2, at least in this scenario, is a critical point. The third one over here in the top right corner shows a cusp. A cusp is not a type of discontinuity, but at this sharp corner, which over here it's showing the sharp corners at x is equal to 0, the function is not differentiable. Because why? Because the left hand limit of the gradient and the right hand limit of the gradient are not equal to each other. So since the function is not differentiable at x is equal to 0, then f dash of x is undefined at x is equal to 0. So the x is equal to 0 is a critical point. So now let's look at the one on the bottom left corner over here. This is an example of infinite discontinuity. This is at an infinite discontinuity, this is an example of a critical point because f dash of x is undefined at this point. And when I'm talking about this point, I mean x is equal to 0 in this scenario. So since it never reaches x is equal to 0, this is infinite discontinuity. So x is equal to 0 is a critical point. Now the image at the bottom, this is a corner. So a corner is a lot like the cusp I showed you over here. A function won't be differentiable at these kind of sharp corners. So it's a critical point, but this type of corner, again, is not a type of discontinuity. So keep that in mind. Now the final image on the bottom right shows a vertical tangent. So when a tangent is vertical, the gradient's not exactly defined. It's basically infinity. So this is a critical point. Again, it's not a type of discontinuity. So the graph of f has a vertical tangent at x is equal to 0. So x is equal to 0 is the critical point for this graph. All right, let's move on to global maxima and global minima, also called absolute maxima and absolute minima. The global maxima is the largest value a function could possibly output for a given domain. And the global minima is the smallest value a function could possibly output for a given domain. For some functions, the local maxima and the local minima also happen to be the global maxima and the global minima respectively, but don't always assume this is the case. So take a look at the graph on the left with the equation y is equal to 2x to the power of 6 plus 4x to the power of 5 minus 3x minus 1. So in the third quadrant, that is over here, the graph moves down to some minimum value before rising up from left to right. This is a point of local minimum because f dash of x is equal to 0 at this point over here. But at the same time, it is also a point of global minimum because if you look at it carefully, you can figure out that this point over here is actually the smallest value that the function f can have. So therefore, it's not just a point of local minimum, but also a point of global or absolute minimum. So in the second quadrant, the second quadrant only, you see that the graph is concave down, and there is a point where the function changes from increasing to decreasing. This is a point of local maximum, but it's not a point of global maximum, at least for this point in the second quadrant, because clearly from the graph, the function can take larger values than the value at the point of local maximum. At the point of local maximum, the graph shows that the function takes some value between 0 and 1, whereas the rest of the graph can also take up values that are greater than greater than 2. It can be 4, it can be 6 for other values of x. So hence, this is a point of local maximum and not a point of global maximum. Now, in the fourth quadrant here, the point which I'm indicating here is a point of local minimum and not global minimum, because the function can take smaller values. But since at this point f dash of x is equal to 0, it's just local minimum. So if the domain is all real values of x, then for this function at least, there is no point of absolute maximum, because technically for all real values of x, the function can extend all the way to infinity if x just keeps on increasing. So you can't define any specific global maxima. So there's no global maxima for this function specifically. So how do we find these absolute extrema using calculus? So the steps are relatively straightforward. The first step is to find all the critical numbers of f in the open interval a comma b. Now, remember again, this is an open interval. Then next you have to plug in the critical values into the original function f. You compare these values of f, and you will find the absolute minimum and maximum by checking which is the smallest value of f of x and the largest value of f of x which you calculated. The smallest value of f of x which you calculated is the point of absolute minimum. The largest value is the point of absolute maximum. Okay, so how do you find the absolute extrema on the closed interval a comma b? Now, the first step is, again, find the critical numbers of f in the closed interval. Apologies, actually. This is supposed to be a closed interval and not an open interval. Sorry for this mistake, guys, but yeah, this isn't supposed to be parentheses. It's supposed to be square brackets. So remember, this is a closed interval. Next, you have to plug in the critical values as well as the endpoints into the original function f. You compare these values of f, and you will find that the absolute minimum and the absolute maximum by checking which is the smallest value of f of x and which is the largest value of f of x that you calculated. Remember, you don't just have to compare the critical points to each other, you also have to compare the critical points to the endpoints as well, because that's very important to understand. All right, let's move on. L'Hopital's rule. L'Hopital's rule involves both limits and differentiation. So the rule is basically that the limit of f of x divided by g of x as x approaches c is just the limit of f dash of x divided by g dash of x as x approaches c. So essentially, if this limit is equal to the same limit, but its derivative you differentiate the numerator and denominator. But you can always apply this rule. This rule only applies for certain conditions any one of these three conditions, not just any one actually, all three of these conditions have to be true in order to apply L'Hopital's rule. So the first condition is that the limit of f of x must be equal to the limit of g of x, and they both have to be equal to 0 as x approaches c. But another possible condition is that the limit of f of x is equal to the limit of g of x, but they are equal to plus or minus infinity. That is to say, they're both undefined. Like, not undefined, sorry, that's too general. But the limit of f of x is equal to the limit of g of x, which is equal to plus or minus infinity. So the second condition that has to be satisfied is that g dash of x is not equal to 0 for all x over the specified interval with x is not equal to c. So that means essentially that g of x cannot be some constant value. It has to be a function in terms of x. It can be a constant, because if it's a constant, then when you differentiate it, it becomes 0. At g dash of x becomes 0, and you can't exactly divide by 0 if you want to get real values. So that should be understood. Now, the third condition that has to be satisfied is that, first of all, the limit of f dash of x by g dash of x as x approaches c must exist. And that's pretty logical because if you want to apply this rule at all, your final answer has to exist in the first place. So yeah, let's move on to average rate of change. This is a pretty simple concept to understand. If you've worked with averages in math a lot, you should understand this. The average rate of change of the function of the function f is a measure of how much a function f changes per unit x over an interval. So this is the general formula. The average rate of change is equal to f of b minus f of a divided by b minus a. Now, also keep this concept in mind because I'm going to be explaining this. I'm going to be using this concept in the mean value theorem, which I'll explain shortly. So average rate of change, you could just say it's the gradient of this blue secant line that connects the points a comma f of a and b comma f of b. So that's just the average rate of change, or the average value of f dash of x. Now let's move on to Rolle's theorem. So suppose y is equal to f of x is continuous on the closed interval a comma c, and differentiable on the open interval a comma c. If f of a is equal to f of c, then there is at least one number b between a and c at which f dash of b is equal to 0. So basically what Rolle's theorem is saying is that for a closed interval a comma c, where we have f of a is equal to f of c, like, hold on, let me show you here. Yeah, so this point over here, which I'm indicating with the mouse, is a comma f of a, and this is c comma f of c, then if f of a is equal to f of c, then there must be at least one stationary point over here. So this is a downward facing parabola, that is a concave down parabola. I've just taken this as an example. So if our domain and range are specified such that we have a comma f of a and c comma f of c, and f of a is equal to f of c, then logically there has to be at least one, there could be more, at least one stationary point in between a and c. That's what Rolle's theorem is saying. All right, here we are, the mean value theorem. So this theorem, as the name probably suggests, is connected to the average rate of change. If y is equal to f of x is continuous on the closed interval a comma c and is differentiable on the open interval a comma c, then there's at least one number b within the intervals at which f dash of b is equal to f of c minus f of a, the whole thing divided by c minus a. So let's use this image on the right here to help explain. I'm going to use this image to help you explain to you. We have a red curve over here with the equation y is equal to f of x. So this, and now we also have a green line over here. This is the secant line. The secant line's gradient, actually you should understand this, the gradient of this secant line, which is connecting the points a comma f of a and c comma f of c, is actually the average rate of change of the red curve from over the closed interval a comma c. So that's the gradient of this green secant. So the purple line is actually a tangent to the curve at x is equal to b, that is at the point b comma f of b. So what the mean value theorem is saying is that it guarantees that for such a scenario, that there will be at least one tangent such that the purple line, that is this tangent, is equal to the average rate of change, that is the gradient of the secant line. So the mean value theorem is guaranteeing that there is at least one tangent such that its gradient is equal to the average rate of change. That's what it's saying. Now move on to optimization. So optimization is basically the process of optimizing or making the best out of a situation. So in such kind of optimization problems, you will have to find the maximum or minimum value of some variable. And they often give real world scenarios when doing optimization. So basically you have to make it the most efficient. You have to minimize something or you have to maximize something. So let's do a problem. A rectangle is inscribed in a semicircle above the x-axis of radius 3 centimeters. What is the largest area that the rectangle can have, and what are its dimensions? So let this line over here, which I'm indicating right now, be x. Okay, we're just considering it to be x because we can change this value over here. We can change half of the length of the rectangle. So logically, because this is half of the length of the rectangle, we can say that the length is 2x. And so they've already told us that the radius is 3 centimeters. Imagine drawing a straight line from the origin to this point over here. Imagine drawing it. And this line over here is equivalent to has a length of 3 centimeters because this is also a radius of the semicircle. So if you notice, since this is since a rectangle has right angles only, you notice that this is a right angled triangle. So we can apply the Pythagoras theorem, given that we know that this is 3 centimeters, and we know that this is x centimeters. So we get to find out that the height of the rectangle, that is this height over here, is the square root of 9 minus x squared. So I've indicated that here. Height is 9 minus the square root of 9 minus x squared. So the area is, you probably already know the area of the rectangle is equal to the length into height. So a of x is basically 2 of x times the square root of 9 minus x squared. So you use differentiation to find the critical values of a, and after differentiating and equating the a dash of x to 0, you find out that the critical value is x is equal to 3 by root, x is equal to 3 by root 2 centimeters. So you just plug this into the function a, and we figure out that a of 3 by root 2 is 9 centimeters squared. So also don't forget, because this is technically a closed interval, given the fact that the height technically can be 0 and the length could possibly extend to the radius, or any other extreme conditions could exist. So we also have to calculate the endpoint. We have to plug in the endpoints into the function. So we figure out that a of 0 is equal to 0 and a of 3 is equal to 0. So we compare all three of these values, and we figure out that a of 3 by root 2 is equal to 9, is actually the largest of the three values. So essentially, the maximum possible area of this rectangle is 9 centimeters square. So we figure out that, then we can figure out that the length is actually 3 by root 2, and the height is 3 divided by root 2, pretty much. All right, so rectilinear motion. This essentially goes into basic physics concepts of kinematics. You should probably already be familiar with displacement, velocity, speed, and acceleration. I'll still cover a little bit of it. So we use S of t typically to denote the coordinate or the position of a point P along an axis. We use V of t to denote the velocity of point P, and we use the absolute value of V of t to denote the speed of point P. And we use a of t to denote the acceleration of point P. Now, remember, these are all functions with respect to time. So basically, that means that S, V, and a these three functions are all varying with respect to time. Or maybe they could just be a constant value, but it depends on the function. So here's some points to understand on the right. They are actually rather self-explanatory. The first one is V of t. If V of t is greater than 0, then S dash of t is greater than 0. So therefore, we say that S of t is increasing. Now, that means if S of t is increasing, then point P is moving in the positive direction on L. Now, the second condition is that V of t is less than 0. If V of t is less than 0, then that logically means S dash of t is less than 0. And therefore, S of t is decreasing. So if S of t is decreasing, that means point P is moving in the negative direction on L, line L, that is. Now, suppose V of t is equal to 0, then because V of t is equal to S dash of t, we say that S dash of t is equal to 0, and that means S of t is constant. So if S of t is constant, then point P is stationary on line L. Then suppose there's a scenario where you have A of t is greater than 0. Since the acceleration is the derivative function of velocity, that means that V of t is increasing. So point P is accelerating in the positive direction on L. Now suppose A of t is less than 0. Then again, v of t is decreasing, so that means point P is accelerating in the negative direction on L. And if you know physics, that you can probably understand that a negative acceleration is essentially just deceleration. So now the final scenario is a of t is equal to 0. So that means v of t is constant. And if a of t is equal to 0, then you should figure out that point P is not accelerating at all on L. Its velocity is constant. Okay, parametrically defined functions. So a parametrically defined function is a function in the form p of t is equal to, in angular brackets, f of t comma g of t. So essentially, there's some intermediate variable t with which we can define two functions in terms of. So we can express x and y as two different functions of t. And if that's so, then you have to just use a formula dy by dx is equal to dy by dt, the whole thing divided by dx by dt. This, if you notice, is just another way of expressing the chain rule. Often in most problems involving parametric equations, at least in my experience, t is used to denote time, so that x and y are together can be used to denote the position on a Cartesian plane, but not always. Okay, let's do a quick problem on parametric functions. This may seem a bit challenging. Find the parametric equations for the semicircle x squared plus y squared is equal to a squared, where y is greater than 0, using the parameter slope t is equal to dy by dx of the tangent to the curve at x comma y. So here's the answer. We have x squared plus y squared is equal to a squared. So since y is greater than 0, we can say that y is equal to the square root of a squared minus x squared. Then we differentiate y with respect to x. And since it's given that t is equal to dy by dx, we just substitute dy by dx with t to get t is equal to minus x by the square root of a squared minus x squared. We do algebraic manipulation, and we eventually end up with x squared is equal to a squared t squared divided by 1 plus t squared. So then x can be plus or minus at, the whole thing divided by the square root of 1 plus t squared. When we substitute this back into the formula for y, we get y is equal to a by the square root of 1 plus t squared. Thank you guys. That'll be the end of this video. Make sure you hit those like and subscribe buttons to see my future videos on calculus. Until then, stay tuned for more videos.